Alright, this is Chapter 2 in Physics and Mechanical Equilibrium. The big idea is this: an object in mechanical equilibrium is stable without changes in motion. So keep that in mind as we go through this section. Here's an example of some rocks that are in equilibrium. These would be in mechanical equilibrium because they're not moving, they're not falling, they're not doing any of that. So this is an example of equilibrium. Alright, so let's talk about force. A force is needed to change an object's state of motion. So if something is not moving and we want it to move, we need to use force, or vice versa. If it's moving, we want to slow down or something, we need a force. So a force is simply known as a push or a pull. So anytime you push or pull an object, that's known as a force, and we need that to change the state of motion. And if we have multiple forces acting on something, we have what we call a net force on the object. Okay, and usually we're going to talk about forces in newtons in here because this is science, and so that's our SI term. If we have multiple forces, we can simply add them or subtract them together. So for instance here, we've got two forces, the 5 and the 10, so the overall force is going to be 15, as you can see here. Or if they're in opposite directions, we're going to subtract and end up with a net force of just 5 newtons. Or if they were in opposite directions and exactly equal, you'd end up with a force of 0. Now here's an example of our young lady holding a rock. Notice that there is a downward force, the Earth's pull, and she is providing an upward force. If that rock's not moving, or if she's holding it still, then those net forces are 0. The exact same downward force as upward force. If we want to talk about force in terms of a spring, we usually talk about it in terms of tension. So tension is our stretching force. We're going to do it, you're going to see on the spring it's usually going to be in pounds or newtons. Once again, most time we'll do newtons. Both of those would be examples of force. So here's our spring scale, and you can see right now it's at 0 pounds, 0 newtons. If we add on a bag of sugar, the tension now in the spring is going to increase. That's going to provide the upward force, and of course gravity would be providing the downward force, and it's going to reach an equilibrium where it's not moving, and on our scale we're just going to say 2 pounds or 9 newtons, whichever. So in that example, the two forces are the tension upward and the weight downward, and like I said, they cancel each other out. They're exactly equal. So you have 0 net force, therefore you have no change in the motion of that object. Usually when we talk about forces in here, we're going to use vectors. And a vector is simply something that includes magnitude and direction. So that's kind of the key thing, is it has both of those. Rather than just saying, hey, we've got a force of 10 pounds or a force of 10 newtons, we're going to also say what the direction is, because that's important. If, we talked about those net forces, and, the net force of 10 and 5, if they're in the same direction, that's a different thing, or if they're in the opposite direction, we're going to get different things. So those are vectors. Scalar quantities are ones which do not have a direction. They only have magnitude. And things like time or area, volume, those things, they don't have direction, so we don't really worry about them. Force, velocity, those would be examples of force vectors. Scalar things, simply ones which don't have direction with them. So if usually we use an arrow to represent the vector. So here's an example of a force vector, 60 newtons to the right in this particular example. And we use the arrows because of that tells us the direction that we're going. When we're adding or subtracting, multiplying scalar quantities, you can just add them. 2 liters of water and 3 liters of water, well, that's 5 liters of water. But it's not necessarily true that you can just add vectors. So, you could add 2 and 3 Newton vectors and you're going to get 5. But what if one is this way and one is that way? You don't get 5 anymore. So direction matters when we're talking about force vectors. All right, so let's talk about, well, that's a wrap up of section 2 on how do you motion. All right, section 2.2 is on mechanical equilibrium. And mechanical equilibrium, we usually write it like this, which means the sum of all the forces equals 0. So when something is in equilibrium, it's not changing its state of motion. All of our forces added together become 0. Okay, so mechanical equilibrium, no physical changes. We can add all these up. That's known as the equilibrium rule. All of those added together must give you 0. So usually it's represented like this, and for those of you who aren't familiar with that little symbol means the sum of. And so we're saying the sum of the forces must equal 0. Therefore, that object is not going to change what it's doing. So here's an example of the guys on the scaffold, and hopefully the sum of all those forces is 0, because otherwise they might be falling or something. So there's the downward forces that you see, the two guys in the scaffold. There's our upward forces, and those must be completely equal to 0, or that scaffold is going to move. Not usually a good thing when you're working on it. All right, so let's think about this. If the gymnast hangs with her weight evenly between the two rings, how would the scale read in both supporting strings comparing her weight? So you kind of did that in the activity. So how would those compare? And then think about, well, what would happen if in the second example she's putting more weight on this one than she is on the other one, and how would those scales read? And hopefully that was pretty easy. You know, in the first one, it would be half and half, and the other one, it would be a little bit more on the one side than the other, but it would still total up her weight, whatever that was. All right, let's talk about the support force. For an object at rest on a horizontal surface, the support force must equal the object's weight. So we're talking about, let's say I have a book laying on a table. One force is gravity, and the desk supplies an upward or support force. Often we call that the normal force. And those two things must be equal, or, you know, maybe if it's too heavy, it's going to break the table, and it's going to fall, and so on. So here's my support force, upward. This is my support force from the desk. This is my force due to gravity, downward. Those two things are equal if that object's not going to change. Like I said, that's often called the normal force, so you'll see that a lot. Normal force is the force up, the supporting force. The sum of all those is going to be 0, once again. And what's actually happening is the book is compressing atoms in the table, and they push back, they push up on that. And that's the supporting force. So the upward support force is as much as the downward pull of gravity. So if you step on a scale, you know, your weight, that's the downward force of gravity, has to be exactly equal to the support force that the scale is putting on you. You know, so when you're getting on a bathroom scale, you're compressing that spring in the scale. So if you weighed 110 pounds, what's the net force on the bathroom scale? Well, the net force has to be 0. You're pushing down 110 pounds, the scale's pushing up 110 pounds. Now, what if you stood on 2 scales and you did it evenly? What would the reading be? And then what if you were on half, you on 2 scales, but you weren't even? Think about what would happen there. Well, that's just like the lab that we did. And so, in the first case, it can be half and half, and the other one, it won't be half. One will be more than the other, but once again, they should add up to total your weight. All right. Now, we were talking, up to this point, we've kind of been talking about objects that aren't moving. What about ones that are? So we're going to talk about ones that are moving, and that's known as dynamic equilibrium, if they're moving in a straight line. So when things are at rest, that's an example of equilibrium. But even things in motion can be in equilibrium as long as there's no change. In other words, they're not accelerating or they're not slowing down, they're not curving, things like that. Straight line, same constant speed. An object under the influence of only one force cannot be in equilibrium. So if there's only, you've got some object here, and there's only one force acting on it, it's never going to be in equilibrium. Force is going to continue to speed that up. So there has to be at least two or more forces to give us equilibrium. So here's this guy pushing the desk across the floor, but if he's moving at a constant speed, there has to be another force. Well, that force trying to slow it down or stop it is known as friction. So that's the force that's pushing against him. And if he's moving at a constant speed, these two forces would be equal. If he's speeding up, then he's applying more force than friction is. But we're talking about equilibrium things right now. So if it moves at a constant speed, it's in equilibrium. The friction force is the same as the force that he's applying. But the sum of those two forces is still zero. All right, think about this. What about an airplane? If it flies horizontally at a constant speed in a straight line, its state of motion is unchanged, so it's in equilibrium. There are two forces acting on the plane. One is the thrust of the propeller, pulls it forward. The other is the air resistance that acts in the opposite direction. Which force is greater? Well, hopefully you said neither one, because if it's at a constant speed, the sum of those has to be zero.